Hello students, how are you? Students, as you know, in the previous lecture I have discussed the formal definition for finding directional derivatives at a particular point, but in today's lecture we will talk about the idea of gradient vector and how we can use the dot product and a gradient vector at a particular point to find the directional derivatives. But before discussing directional derivatives, I have to discuss the gradient vector. Let me write its definition first. Its definition says that the gradient vector, or simply you can say gradient, of particular function f of x y at a point p naught x naught comma y naught is the vector gradient of f is equal to partial f by partial x I unit vector plus partial f by partial y j unit vector is obtained by evaluating partial derivatives of f at p naught. Okay, this is basically the formula for finding gradient vector. Its definition, let me explain it again. Its definition says that you need to find the gradient vector of your function at some particular point, and you are also given that point. Okay, then when you find its gradient, then it will become equal to, first of all you need to take the partial derivative of your function with respect to x, and then you need to find the partial derivative of your function with respect to y, and you have to also mention the components with it, I component and j component, and it is obtained by evaluating the partial derivatives of f at the point p naught. This is the same that I have explained earlier, that you need to find the partial derivatives. Okay, but now I will write the theorem for finding directional derivatives, and we will discuss both these ideas in one example, and I will explain the gradient vector in this example, in that example, and also the directional derivatives. Now for example, students, we have a theorem. The theorem is basically about the directional derivative is a dot product. The directional derivative is a dot product. Now students, the theorem says that if you have a function f of x y is differentiable in an open region containing p naught x naught comma y naught, then df by ds you means, as I discussed in the last lecture, that we need to find the directional derivative in the direction of some unit vector. So basically this u represent here the unit vector, and p naught represent the point at which we are trying to find it. Okay, and it would become equal to gradient of f at a point p naught times u vector. Means you need to find, first of all you need to find your function's gradient and at a particular point, and then you need to take the dot product with the given unit vector. Okay, which is basically the dot product of gradient of f at p naught and u. This is as I explained here. Okay, and this is the formula for finding the directional derivative at a point p naught in the direction of a unit vector u. Now student, let me explain an example, and I will explain that how you can use this theorem. Now students, see here, basically there is a condition on our function that our function should be differentiable, means your function should be continuous on that open region, and also its derivative exists at that point, because otherwise we will not say that its directional derivative exists, because if it is not differentiable, definitely it is maybe it is not continuous, or if it is continuous, then we are not sure about whether it is differentiable or not. Okay, now students, the example says that find the derivative of f of xy is equals to x e raised to power y plus cos of xy at the point, yes, now it is visible, at the point 2 comma 0 in the direction of v vector is equals to 3i vector plus 4j vector. Okay, now students, let's see its solution. You know that here we are given the vector v vector. Okay, this is basically not a unit vector, but you know the definition of a unit vector, because in this definition, for finding directional derivatives we need a unit vector, and you know unit vector is equals to u vector is divided by u vector magnitude, or you can say v vector over v vector magnitude. So that's why first of all you need to find v vector's magnitude, and it is equal to 3 square plus 4 square, means its x component square plus y component square and square root. And if you evaluate it, then you will get 25 inside, and after finding its square root you will get 5. Okay, so its unit vector will become equal to v vector over v vector magnitude. So 3i vector plus 4j vector is divided by 5, and if I separate 5 with both of them, then I will get 3 by 5 I vector plus 4 by 5 j vector, or you can also place the hat on both of these, because now it is equals to the unit vector. Okay, and this is our unit vector, and now as you know that here I need to find the gradient of our function. Okay, and the definition of gradient says that you need to find the partial derivative with respect to x and with respect to y, and you also have to mention I and j with this. Okay, now your function is basically f of xy is equal to x e raised to power y plus cos of xy. Now students, if you find its gradient, then you can write here gradient, or means apply gradient on both sides, then you will get e raised to power y plus cos of xy. And now you know the gradient definition says that you need to find the partial derivative, means partial by partial x I unit vector plus partial by partial f by partial y. Sorry, I will not write here partial f, because now it is applied on our function j vector, and x e raised to power y plus cos of xy. Now you will write it as partial by partial x e raised to power y plus cos of xy times I unit vector plus partial by partial y into x e raised to power y plus cos of xy. Okay, and also you will write here j unit vector. Okay, now if you find its partial derivative with respect to x, then here the derivative of x will be 1, and you will get simply e raised to power y, and you know the derivative of cos is equals to minus sine xy, and the derivative of its angle would become equals to y simple. Okay, and here I unit vector, and in the similar way you will get x e raised to power y minus sine xy times x times j unit vector. Okay. Now students, as you know that you are given a point and that point is 2 comma 0, and you need to find your gradient of your function at this particular point. So I will substitute this point in this both of the values in place of x and y. E raised to power 0 minus sine of 0 into 0 means, definitely if I write here 2 times 0, then it will become equal to 0 I unit vector, and plus 2 e raised to power 0 minus 0 j unit vector, and you will get I unit vector plus 2 j unit vector here. Now you also get your gradient vector. Now from the definition, students, you know that you need to apply the dot product on gradient of f at particular point times u unit vector. Now student, this is our vector, and here I will write gradient of f at particular point 2 comma 0 times u unit vector, and it is equal to this one I unit vector plus 2j unit vector into 3 by 5 I unit vector, or let me check my function again. Yes, 3 I unit vector plus 4j unit vector, and I will get plus 4 by 5 j unit vector. Okay, if you take the dot product, then you will get here 3 by 5 into 1, because I dot I would become equal to 1. Okay, I will write it here as I unit vector dot I unit vector, and plus 2 multiplied by 4 by 5 times j unit vector dot j unit vector, and their dot product will become equal to 1, and here I will get 3 by 5 plus 8 by 5 and 11 by 5, and this is your desired answer. Okay, and in this way you can find the directional derivative by using the dot product and the gradient vector. Student, in today's lecture I have explained about the gradient vector, and also I have explained that how you can find the directional derivative informally, because in the previous video I have explained that how you can use the definition of a gradient vector for finding it. But now you can also use the definition of gradient vector and a particular theorem, and this is the easiest way to do it. Okay, now student, this is all about today's lecture. See you next time. Thank you.